Okay, so we're going to do some complex analysis now, and we've got a question here using the estimation theorem. So it's telling you what theorem we're going to use. We're going to find an upper estimate of this integral on z equals 2, so the modulus of z equals 2, for the conjugate of z squared minus 1, z squared minus 1 dz, and it's the modulus of this integral. So what is it that we're actually looking for? Well, basically what we're looking for is, as it's an upper estimate, we want to find the largest value using the information that we've got that this integral could equal. And as it's a modulus, then the answer is going to be a real positive number. Okay, so the estimation theorem. So to use the estimation theorem, inside this integral here, this has to be continuous on its domain. So what we see here in the denominator, we've got z squared minus 1. So we need to eliminate a couple of points on the domain before we can continue with the estimation theorem. So what we can say, let's say here, f of z, if that equals the conjugate of z squared minus 1 over z squared minus 1, is continuous on the complex plane except for when this is 0. So z squared minus 1, just go over here for a little scratch work. Z squared minus 1 equals 0, z squared equals 1, therefore z plus or minus 1. So it's continuous on all the points in the complex plane except for minus 1 and plus 1. Okay, so now we can continue with the estimation theorem. So what does the estimation theorem say? So the estimation theorem tells us that the integral on a contour gamma, so in this case our gamma is the modulus of z, so we can put that there, of a function f of z dz, and we've got these lines here to denote that we're looking for the modulus, so that is going to be less than or equal to m and l. So what is m and l? So m is going to be our maximum value that we can come up for this function, and l is going to be the length of gamma. So the length of gamma we can do pretty quickly, that's pretty straightforward. So basically it's just a circle with radius 2. That's going to go 2 there, that's our real, and that's our imaginary, and it will go in an anti-clockwise direction. So what is the length of L? Well, L is just basically 2 pi r, so the radius is 2, so that's 4 pi. So that's pretty straightforward. So now we want to find an upper estimate for this function. So for that we need to find the maximum value for the denominator, for the numerator, and the minimum value for the denominator. So therefore if we use the triangle inequality, so for the numerator, let's find the normal triangle inequality for conjugate of z squared minus 1. Okay, so triangle inequality, the standard version, will say that this is less than or equal to, so we can't put an equal sign here, will make no sense whatsoever because we're dealing in complex numbers. So for example our z here, our z could equal 1 plus I. So 1 plus I will be inside the contour here, so that will count. So we can't say that that is bigger or smaller than something else, we have to continue with the modulus. So now what we do is we just break this modulus apart a little bit, and we say conjugate of z squared plus 1, because we're trying to find an upper value for this. Now we can say that we're going to do something with this conjugate of z. So the conjugate of z and the modulus of the conjugate of z, let's work it out what we would have if we had the conjugate. So z would equal 1 plus I, for example, and the conjugate would equal 1 minus I. So therefore the modulus of z in this case will be the square root of 1 squared plus 1 squared, which is square root of 2. And in this case, the conjugate of z would equal the square root of 1 squared plus minus 1 squared, which again is still square root of 2. So we can eliminate this conjugate sign here and say z squared plus 1. Now what we're going to plug in for z, well, we'll say that z is the modulus, sorry, the modulus of z is 2. So if we just plug in a 2 here, we can now put an equal sign because we're going to get a real number. I'm going to say that is 5, and that's by the, actually I just put by the triangle inequality. Okay, now let's go with the denominator. So now for this, we work on the backwards triangle inequality. So what we're looking for now is the modulus of z squared minus 1. And then we can put that in 2 modulus signs. This time we change the sign because now we want this to be larger than or equal to something. So we change the sign to this way around. And now we keep the outside modulus, and inside we distribute this modulus to each one of these. So we go z squared minus 1. Okay, so keeping this modulus here, z squared, again we know that z is 2, so we can say that this is less than or equal, get the right direction, is greater than or equal to the modulus z squared will be 4 minus 1, which equals 3. So these are our 2 important values that we've got here, and this is by the backward triangle inequality. I'll just put TI for short. Same thing there. Okay, so we've now got a 5 and a 3 for the values of this f of z in the denominator and numerator. So that will give us our m. So here we're looking for the m and the l. We've got our l, which is 4 pi. So therefore our m equals 5 over 3. So we've got 5 and 3. So now we've got m times l. So therefore m times l equals 5 times 4 pi over 3, which equals 20 pi over 3. Okay, so what we can say is then that by the estimation theorem, so by the estimation theorem, I'll just put that for short, so we know what we're talking about, this is the question we've got. We can say that the modulus, upper estimate that is, of this function here, so that's the integral of gamma, with assign gamma to the modulus of z is 2, conjugate of z squared minus 1 over z squared minus 1 with respect to z. Okay, so now what we can do, we can say that this is equal to 20 pi over 3. So that's the upper estimate. So upper estimate. So what we're saying is this is the maximum value that we can attain for this modulus of this function here. Okay.